So today's lesson is about complex fractions. We're continuing on in the review material, the chapter R material. If you're following along in the book, this will start on page 51. All right, so a complex fraction means you've got a fraction within a bigger fraction. So you can have any amount, more than one fraction though within your fraction. So here we have 1, 2, 3, 4 terms. If you counted them all together, we could consider this a problem divided by this fraction another problem. So there's two methods to work this. You may have seen this in your past, and maybe one method you prefer over the other, but I'm going to explain both. One way to think about it is work the top like we learned in previous sections. Combine those fractions by getting a like denominator, work that out. Then do this as a separate problem, work that out, and then do the divide last and multiply by the reciprocal. So that's one method for doing it, probably the most straightforward. But the quicker way to work it would be to multiply everything we see in this big complex fraction by the overall LCD, or the super LCD you might call it. So remember, LCD means the least common denominator, the least thing that any of these denominators, that's just over 1 and that's just over 1. So when you look at your 4 terms, the only true denominator besides 1 is just this k. So k will work. K will be the LCD, the least thing that every denominator will fit into evenly. So I'm going to times everything in the numerator by k and everything in this denominator by k. And so I'm keeping the balance, which is always important when we work fractions. We do the same thing to top and bottom of the fraction, and also when we solve equations in the next chapter, we know we keep equations balanced on the left and right. So that's always a principle in math class that we will always hear that throughout. So I'm timesing the top and the bottom of this super fraction by the LCD k. So we know when we multiply that we can distribute the multiplication, so it distributes out to each term. So when I distribute it on this first term, we've got a 6 times k, or 6k. When I distribute it to the second term, though, something good happens, and that's these k's are diagonal, so they cancel out, and just leaves the minus 5. Thus giving me a nicer, cleaner problem, getting rid of the complex part of it. Same thing on the bottom, because I have picked the LCD, these denominators should all disappear, and I won't have the complex. So timesing by k, distributing it, k times 1 is just k, or 1k, and k times 5 over k, again these are diagonal, that's k over 1, so that is truly diagonal. Common factors can be canceled out, just leaving plus 5. And then you're actually just done with that. That would be the answer. Alright, so that's the easier way to do it, I think. Like I said, I would show you both methods. So the other method is to think of this as two separate problems. You got your numerator, 6 minus 5 over k, divided by this original denominator was 1 plus 5 over k. And so we'll work each part, the numerator, denominator separate, and then apply the division. So in that case, if I were going to combine these, I would need a like denominator, which would be the k. So I'd rewrite both of these with a common denominator, k, that's the LCD of those two. So this stays the same, but remember we have to say whatever we did to the denominator, you have to also do to the numerator. So this 1 became a k, so it's been times by k, so times the top also by k, making it 6k. So that becomes 6k minus 5 over the common denominator we found, k. So that simplifies the numerator. Then we jump over here and do the denominator. Same thing, I need a like denominator, which is k in this case. Again, 1 into k is k, k then times the top also is k, and also just notice 1 over 1, k over k. They're equivalent. They're both forms of the number 1, so we haven't changed the value. Here nothing has been changed, so don't change the numerator either. Now that we have a like denominator, we add k plus 5 in the numerator over the common denominator k. Now this is a division problem, so what we learned in a previous section is that division can be changed to times by flipping the second fraction. So let me make room for that here. So now we're going to write our division, 6k minus 5 over k, divided by, we'll change to a times, and we'll flip the second fraction. and then we'll work it like we've done in a previous example. If there's anything factorable, we should always factor. But here, the only thing we can do is diagonally, since you're multiplying, you can cancel any diagonal common factors. And so then that leaves 6k minus 5 over 1 times k plus 5, or just k plus 5. Same answer, notice, with either method, so whichever one suits you the best. I think this is a little faster though, this method, but it's kind of a mess, I guess you could say, in the way that it looks. But the concept was I times the top and bottom by the super LCD, whatever the LCD of every fraction in my problem was. And I'm going to use that again on my next example. All right, so the next example looks like this. Now, a question you may have is, can't I just cancel some things out? Couldn't I simplify this before I do all that mess? And you cannot. If this were times, when we're multiplying, we can cancel away. But if there's a plus or a minus sign between our numbers, then you cannot cancel with add and subtract. You have to condense it down and try to factor or something. So no, there's no way to kind of simplify it that way. So we attack it. It is a complex fraction. We have 4 true, what I would call more true fractions here. So the LCD, I'm going to use that method of the super LCD of every fraction you see. I need one of every type of denominator, so I need this a plus 1. That's a set, a quantity, a plus 1. And then a is a totally different quantity, so I'm going to need each of those, a and a plus 1, each of those factors for these to both fit into it. And then the denominator, I've got the exact same thing, so that's going to do it for that as well. So remember, once you determine the LCD, which again is what every denominator will fit into evenly, so this fits into it with some leftover, this fits into it with some leftover, but these both fit into it. So if it's going to fit, you're going to have at least one of each type of factors or parts you have in your denominator. And then these fit into it. So that's the least thing all denominators fit into the LCD. So we times it to the top and the bottom of the fraction, the numerator and denominator. Remember that this multiplication distributes, so we can multiply by every term basically. When we times it by this term, the good thing that's going to happen is the denominators are going to cancel out and get rid of the complexity of it, the complex fraction. So it cancels on the diagonal, leaving an a times a left over, or a squared. When I distribute here, the a part cancels, and you're left with the a plus 1. So just the a's cancel. And then 1 times a plus 1, a plus 1. And there's no denominators. Then moving down to the denominator, also timesing these both by the LCD, so that distributes. When I distribute it here, the a's cancel, so I have 1 times a plus 1. And then distributing it here, starting over each time, the a plus 1 part cancels, so you've got 1 times a, or a. So we have a couple of a's that can be combined there. We could call that 2 a's, 2a plus 1. We always think about, is there any way to factor this? You know, these trinomials sometimes will factor. This one does not, but we should think about it. Nothing reduces then. We can't cancel out these loose plus and minus signs. We can only cancel if there was a way to factor it first. So that is your final answer. All right, let me give you another example. So what I would encourage you to do with this one is pause the video and try to work it on your own before I work it out for you. So here's my next example. And it'll be just like the last one, so if you'd like to pause the video now and try that, I would encourage you to do so. Alright, so using the idea of the super LCD, this is over 1, this is over 1, so there's really just one denominator term, which is the y. So we're going to times everything through by y. The numerator times y, the denominator times y, which will basically mean every term times y. So y times 2 is 2y. y times 2 over y. The diagonal y's cancel, so it's just 2. In the denominator, y times 2 is 2y again. Notice the 1 is there, so 1 doesn't really change anything. It's just kind of a placeholder for the denominator, but it's not canceling anything out. And then distributing it here, the y's cancel, just leaving me a 2. We should see if I can reduce this by factoring. I always mention that. This one I think actually will. You can factor a 2 out of the top. You can factor a 2 out of the denominator. And then these parts don't match, but the 2's can be canceled. The vertical 2's are a common factor, leaving you a y minus 1 on the top and a y plus 1 on the bottom for your final answer. Okay, let's try one more. Which again, I'll encourage you to pause the video and try on your own before I work through it. Alright, so we want to times through by the LCD of all of the fractions. We've got an x and an x plus 1, which are different factors, so I'll need one of each of those. I need the x, I need the quantity x plus 1. And then here in the denominator, x will also go into x, so I'm covered. Every denominator I see, all three denominators, will fit into that LCD, and that's the goal. Then I times top and bottom by that LCD. Multiplication, because we are timesing, we're multiplying, it distributes into each part, each term. So over here on this first one, when I times it by the LCD, the x plus 1 parts cancel. You have 1 times x, or just x. When I times it to the second fraction, we start over with the full LCD. And the x factors cancel, which leaves a negative 1 times x plus 1. Looks like that. In the denominator, when I times this by the LCD, the x's are diagonal, leaving 1 times x plus 1, or just x plus 1. I'll drop the parenthesis on that since there's just a positive 1 to distribute in front of it, and that won't change anything. On the top, I had a negative 1 to distribute, so that is important. So I will need to complete that process and distribute the negative 1. And then this will reduce. X minus x is 0, so I just have minus 1 over x plus 1, and that will be your final answer on that. Okay, let's do one more example. If you'd like to pause the video, free to do so and practice this. So sometimes you have to factor, and we've seen this in our past lectures, that sometimes you have to factor before you can find the LCD. If there's any quantity like this that isn't in its prime parts, you'll need to factor. So y squared minus 9 will break down into y plus 3 times y minus 3. It's equivalent to that. So we could rewrite it as y, or y over 1, plus 1 over y plus 3, y minus 3, in factored form, and it's over 1 over y plus 3. And then I can more clearly see what my LCD needs to be. I need the y plus 3 for this to go into it, and it's already there as well, and the y minus 3. So I will need to times the numerator and denominator by the LCD, or super LCD, y plus 3 and y minus 3. And again, the idea is every denominator should fit into that. Then when I distribute, nothing cancels here, so I'll have y plus 3, y minus 3. But when I distribute here, it all cancels, just leaving a 1. In the denominator, when I distribute here, the y plus 3's cancel, so you've got 1 times y minus 3. Then this is going to need to be cleaned up. I'm going to need to FOIL this and distribute the y, and then add the 1, and it will be over y minus 3. I'm not going to have time to finish the cleanup before the video times out, but that would be the process to finish that.